rock domain for the SLB Reservoir Labs. Reservoir Performance Department is based out of Houston, Texas, and the technical representative for the rock labs for the Western Hemisphere. Prior to joining SLB in 2013, Barbara was a college professor in geology for 25 years, uranium exploration consulting geologist, and hydrogeologist, and a production geologist for a major oil company. Barbara holds a PhD degree in geology from Syracuse University, where her research centered around inorganic chemistry, geochemistry, and radiogenetic isotope geochemistry. A Master of Science degree in geology from California State University, Long Beach, with research in hydro and biochemistry, peat, and Master of Science in geology from Oklahoma State University. Barbara has been a member of the AAPG and GSA for over 35 years. Is also a member of the SPE, SPWLA, SCA, and Houston Geological Society, where she's a past director in her spare time. She tutors high school math, builds bunk beds for charity. In addition, she is one cat shy of being the crazy cat lady. Please welcome Dr. Barbara.
Thank you. I always get asked how many cats do I have, and I always say I'm one shy of being a crazy cat lady. It's always one shy. It doesn't matter how many I have. I'm always one less. Okay, if I can remember how to use a Mac, I will do this. I want to thank Bill and Tali for extending this invitation to me to come and talk to you today. To me, it is truly an honor. I'm a born and raised Okie, but I'm also a New Yorker, having lived there about as long as I lived in Oklahoma. I very shamefully said I did not know much about the Native American tribes in Oklahoma, even though my entire education from 3rd grade up through my first college degree was in this state, and I did very well in my Oklahoma history. So I thank you so much for educating me over the last 4 years since I've gotten to know Tali and even Bill a little bit more now. But thank you for that. I wish I knew how to say thank you in Osage, so somebody out there can say it for me. I didn't hear it, but okay, we'll get it later at the end. So anyway, thank you again. And with that, I want to start. My title says New Opportunities Through Carbon Capture. It's a little bit of a misleading title because when we're asked to do abstracts, we're not really sure what we're going to end up with. And so it is some new opportunities, but it's also along the lines of other parts of this, and I do represent the Reservoir Lab, as you can see on that. That means that I am a lab rat. I'm also, I moved out of that and I sell what we do, but I'm a lab rat, so we actually I'm going to be talking also what it takes for you guys in the Osage Nation to get a permit. And it's not as easy as saying, well, it may be eventually, depending on whether you get in, if you get kind of primacy, but it's not as easy right now with the EPA to just go in and say, we want it. It takes about a year's worth of work to go into the data analysis, and then it takes another at least 2 years. They keep saying they're going to cut that down, but they haven't. At least another 2 years to get the permit. So it's not an easy short-term thing to do. So with that, I want to just go very quickly what I'm not going to, or just let you know it's not just going to be what we're doing in the opportunities or what they are, but I want to talk about why carbon capture. And I think that that is more, as we did this morning and even some yesterday, it's more of a background type of information to go through that. Some opportunities for what I saw from the Osage Nation. These have already been talked about, so I'm not going to dwell on those. And also, as I said before, I don't know a lot about the nation or the geology here. I am an Okie by trade. I understand the geology of Oklahoma, but I'm learning a lot more about it because when I started in this industry in the early 80s, Jim, those 1962 logs, even though they did not really seem old to me at the time, they are now. But what the opportunities are, we've already talked about those, so I don't have to belabor that. Those are just things that I had found and that I thought about. I am involved in projects with hydrogen, lithium, carbon capture, carbon or EOR, so the CO2 EOR applications, as well as oil and gas. So I'm involved in a lot of different things. I see a lot of different projects throughout the world, and I was thinking that perhaps some of those might be applicable here. I want to talk about the role of the laboratory analysis, hopefully take it down to a level to where everyone can understand it, and I don't mean to do that derogatorily, but I'm used to speaking with people that are at, like, I can talk to Jim and we can talk about what's detrital and what's not and why, but that doesn't help you if you're just trying to understand that you're either going to make some oil or you're not. And then the use of digital analysis, we haven't really talked about that, but that's where the future is going. And then I want to very briefly talk about lithium, because I am involved in some lithium projects, and I think that's a very interesting teaser in there. So with that, why carbon capture? Well, if we look at the energy consumption, the global energy consumption, right here, what you will see in 2020, the global consumption was somewhere around 600 quadrillion British thermal units, and that just means it's a lot of energy. Most of that is fossil fuel in 2020. Granted, we had a little bit of a decrease in 2020 because of the lack of industry, because of that thing called COVID, but we do still have most of that is fossil fuel. If we go over to 2050, and you'll see why we all use the target date of 2050 now, we go over to that 875, 900 quadrillion British thermal units. Again, a lot of energy. And that energy is still going to be mostly fossil fuels, predominantly fossil fuels. There is going to be an increase in renewables, a very large increase in that, but the increase is still going to be quite high overall. So while we say that there is an energy transition, and there is an energy transition that is going on, it is being fueled by fossil fuels. So while people say we're going to get rid of all of this, yeah, that's kind of nonsense. It's putting your head in the sand and ignoring the reality of the situation. There is an energy transition going on, but it is being fueled by fossil fuel. So just so we all know where I'm coming from, I'm still going to talk about carbon capture, and I'm going to talk about carbon. So with that, why carbon storage? Why are we talking about carbon? Well, the reason is, and we saw that this morning, I think this was the exact same diagram that we saw this morning, and that is the global carbon emission. If you look at back when we had coal and wood, going up here, a fossil fuel would be coal, not wood, but it's a lot of carbon that's being put into the atmosphere. And if we look at what that carbon is, the carbon is involved in what we call the greenhouse gases. And these are the gases in our atmosphere that regulate our temperature at the surface. And those greenhouse gases are made up of carbon dioxide, and it's about 76% carbon dioxide, and that is both from fossil fuels, industrial processes, and then the forestry and other land uses. And you can tell the difference in whether or not the carbon in the atmosphere is from a fossil fuel, or it's from a tree burning in a forest, or just your forest itself. We look at the carbon isotopes, the carbon-12, carbon-13, and carbon-14, and we look at those ratios. I say we, I don't do this. There's a lot of researchers that do it. I'm just talking about research does this. So you can tell the difference. And just to kind of jokingly say here, I have joked around and said, yeah, but what about the volcanoes? Humans put at least 60, it's either 60 or 600 times the amount of CO2 into the atmosphere in a single year than any total amount of volcanic CO2. At least that was what I wanted. I looked it up last night to verify because I had a brief little joking conversation yesterday about it. So these are mostly human. These are human right here. Methane, 16% of our greenhouse gases are methane, 6% are nitrous oxides, and then the fluorocarbons, the fluorocarbon gases, about 2% for that. So if we look at this, I've already explained you can tell the difference in the CO2 and the sources of it, but I want to very briefly talk about methane, and I noticed later on today there's going to be a talk about methane. When I put these together, I had no idea what other people are going to be talking about. I didn't even know who else was going to be here until I saw the program yesterday. So this is just coincidental, and I think it's interesting that we're all kind of thinking along similar lines. But methane itself is actually worse as far as a greenhouse gas goes. It traps more heat than CO2. It is 80 times more harmful than CO2, and this is one of the reasons that we try to decrease the amount of methane going. The methane leaks are a big deal in the oil industry, and I work at, I'm going to say Schlumberger, We're no longer called Schlumberger. We're no longer called an oil field service company. We are an energy transition company. So we have completely rebranded. It's been over a year, and a lot of the research dollars within the corporation that I work for is going towards energy transition. But our biggest amount of revenue comes from oil and gas still. So we are trying to help decrease methane, the flaring of methane, to stop that before it happens because of the methane in the atmosphere. Methane is not as talked about as carbon is, because carbon is much more abundant. Methane has a residence time of 8 years in our atmosphere, about 8 years in the atmosphere. Once it's in there, methane is CH4, pure methane. So carbon and hydrogen, CH4. It combines with the oxygen, and it's going to oxidize to form CO2 plus water. So even though it starts out as methane, 8 years later it has transformed into, chemically it's transformed into CO2, so it's adding to our CO2. All right, so why do we do all of this, or why are we talking about it? That's because of the Paris Accord. And I'm staying away from politics, I'm just giving you what's the state of the world today. This was a global agreement that was signed in 2015, December of 2015, by quite a few of the nations, and even more have signed on since then. And this is to tackle climate change and its negative impacts. And what they want to do with the Paris Accord, or the Paris Agreement, is to substantially reduce the global greenhouse gas emissions and to limit global temperature increase in this century by 2 degrees Celsius. And to do that, we need to have a net zero emissions of carbon by the year 2050. I love the little wedge illustration we saw this morning, because that's what a lot are saying. It's, yeah, I'm not going to talk about that, but the goal is to reach this zero emissions by 2050. And in order to do that, we have to have underground storage. It's not that we have to necessarily decrease what's being produced. We have to somehow get it out of our atmosphere and put it into an area where it would not be in the atmosphere to go up into acting as a greenhouse gas. So we want to store that to permanently get it away from the atmosphere. And so this is what is needed to meet the net zero. Today, we are storing about 46 megatons of CO2 annually. And in order to meet the net zero, that has to exponentially increase to 7.6 billion megatons. So it's our 7.6 billion tons, or metric tons is what I meant here, of CO2. So it's a major increase, and we're not getting there. We're not doing it yet. But this is why companies are going for those large hubs. We saw that yesterday in one of the talks, and just very briefly about a hub in the Gulf Coast. This is why the companies are putting in these very large hubs where a lot, 4, 5, 6, 7, 8 large major companies, oil producing companies, are going to a hub to sequester and put the CO2 they're producing from the refineries along the Gulf Coast and along these different producers, putting that CO2 back into the subsurface, generally into those Miocene sandstones, which are very, very thick sandstones, and very, they're unconsolidated. They are not fun to try to core or to try to analyze. You have to, once you get, if you're able to get it to the surface, you have to keep them frozen at the surface somehow. You have to keep them solid, and that's very hard to do. All right, so we have underground storage. We need underground storage. So what are the opportunities for the Osage Nation for this storage? And the reason you have that opportunity right now, or not the reason you have the opportunity, but the reasons you should take advantage of that opportunity right now is through these tax incentives. And these have been talked about a lot already. It's from the 2022 Inflation Reduction Act. You do get money, you do get credit, you do get money for this, but for every ton that you put into the subsurface, either $85 or $60, depending on whether it's permanent or it is temporary. And I thought, because Tracy is here, I thought he did a good job talking about that yesterday. Gary mentioned it yesterday also, so I don't have to belabor that. If you're going to do direct air capture, and one of the problems that was discussed yesterday was that not always able to just buy some company's emission, or they don't want to sell it, or they don't want to pay you to get rid of it. Some companies just don't want that. So instead, what corporations are doing and what researchers are doing right now, and it's still in a research phase, is they have direct air capture, or DAC. Direct air capture is where you have a large, basically a big membrane that you put out into the open air, and it simply brings in the atmospheric air, filters it, sequesters or captures the carbon in that. And this is a very simplistic view of it, by the way. It's much more complicated than that. But the basics is that it captures it, and then they take that carbon and they sequester that carbon. So you still have to store it. So you have to do something with that carbon. But it's another way to do it, and there's a lot of research going into it. They're being paid a lot because it's still in a very infant stage. Oxy is putting in a direct air capture program in the Permian Basin. The company that was building the actual filters they're using was not building them fast enough. They ended up and trying to get them to them because they had other clients also, so they bought the company to build their own now. So it's just one way of all the money that's going into this problem with the carbon in the atmosphere. The caveat of all this is that you have until January 2033 to begin construction. So, Osage Nation, I'm not going to even really go into this. This has been talked about a lot, and you guys know a whole lot more about the North Burbank unit. This is a CO2 EOR flood area. It has been successful in what it is doing as far as production. This is straight out of an the EPA 2020 document. I'm sure it's changed since then, but this is just some of the stuff that's available. But it is something that's already going on, and is something that is an opportunity as far as the credits or the financial part of that, the incentives go. The Osage Nation, also the CO2 storage in the Arbuckle. They're wonderful. I thought it was a very good paper that was by the Oklahoma Geological Survey. It did have some, it might be controversial, and I'm not really sure why it's controversial. There are some things that weren't entered as far as some of the data analysis, the laboratory analysis that would need to be done, but I thought it was an excellent start to show what can be done on the Osage Nation as far as permanent storage. And the Arbuckle is the one that's mostly being looked at. I did want to emphasize something in here. In order to have the storage, permanent storage, you have to have a depth that allows the carbon dioxide to be at the supercritical state. It has to be in the state where it acts as a gas and a liquid. So it has to be in that state. So you have to have a certain depth to have the pressure that you need. And yesterday the depth was like 3,000, 3,500. I've seen that. But the calculations I do, it's around 2,500 feet. You've got to have that depth. What I'm saying is it can't just be one of those higher sands that Jim was talking about. It's just not going to work with keeping it in the supercritical state. So this is readily available online, the references right there. And by the way, it's January 2024, so it's technically not even the right year for it, but it's coming out in January. It's already out in Fuel. It's available online, but it's their January issue. All right, so the next one is the role of laboratory analysis for the Class 6 permits. So putting this into the Arbuckle or into any other formation, you've got to have a Class 6 permit in the U.S. in order to do that. And what's involved in that? For the assessment of a site for CO2, and this is where our lab gets involved, or where the company I work for now, SLB, gets involved. And we would start out with a site, and this is a site that would produce CO2. It can be an electric plant, it can be a fertilizer plant, anything it can be just a paper mill type thing, but any plant that produces CO2, you have in the subsurface, and this can be the subsurface that is directly under the plant. I'm working on a couple of projects in South America right now where it's literally right under the plant, but I'm working in others where it is 100 miles away. So the subsurface is going to have, generally is going to have a very key component, which is the fresh drinking water aquifer. And this is what's causing a lot of the problems. This is why you have the regulations you have, is to protect that drinking water aquifer. And that is why I put that up there first. I want people to realize that's what's really being protected, as well as the public above it. But we have to protect our drinking water. So with this also, where you have a site assessment, you're looking for a reservoir. And the reservoir is where you're going to inject the CO2. So that's your reservoir. But in order to inject the CO2 and keep it in the subsurface, you have to have a cap rock, or what we'll also call a seal. And those are the shales, the mudstones that Jim was talking about that can cause problems if you have them in your sandstones. They won't give you as much of a reservoir as you want if you're trying to inject in that. But if you have a nice thick mudstone or shale above it, that's great. Some of these can be limestones. Also, they're very tight limestones. We're looking at that tightness in there. We don't want the CO2 to permeate through it. So with both of these, if you have your reservoir and your cap, what you would do is you will inject the CO2 into the subsurface in an injection well. Just like you would if it's CO2 for EOR, you're going to have an injection well. But instead of having a producing well in EOR, you're going to have a monitoring well. And that monitoring well is where we're going to monitor it to see where the CO2 front is going. Where is that underground plume of CO2 going? Because we're pushing the water away, we're pushing whatever else may be in there. There's usually salt water in these most often. We're pushing that out, and we want to know where that CO2, is it going where we want it to go? So you have a certain number of monitoring wells to actually figure out where it's going. These are still, again, in the infancy. There's only been 2 projects, one very long-term project in the US where we've been able to monitor it. So at this point, it's all still in the infancy, but we have the knowledge, we have the expertise from the EOR applications because we've been doing that a long time. All right, so once we have all of this, we will monitor it, and then these little lines right here, these little wells right here, these are basically seismometers. They're in the surface with seismometers with cables and everything attached to them, subsurface lines in them, fiber optics on it, to tell us whether or not you have an event. They can also tell you if you have certain isotopes or certain tracers in there on whether or not it's hit that area yet, depending on what you have in your fiber optics. So with all of that, it all boils down to basically what we're looking at is we're looking for a seal or a containment, we're looking for storage, and then we're looking for the rock properties to tell us whether or not it's going to transmit it or even allow it to go into the rock you want. And the workflow is not that simple. The workflow involves a site assessment, which usually starts with seismic and old well logs. I've been in rank wildcat areas. I've worked on those with clients where the nearest log was over 100 miles away. That's not very close when you're trying to get an analogy, but it's still these rank wildcat areas in some cases of the world. So they had to use seismic interpretation with the seismic lines they had. We used drill data. We've drilled a well now and looked at that. We take whole core. We take sidewall core, which are little ones, whole cores, where you actually go and you drill like a 3 or 4 inch core. Usually they're 3.5 inch or so. You take the core, the actual rock out of the ground. Sidewall core is usually 1.5 inches, or it can be as little as 1 inch, 0.92 inches, and we take it into the side of it, so it's a horizontal core. Or we also use cuttings, and usually it's a combination of all 3. But in the realm with the permitting application, you have to also have the geochemistry of your fluid. You have to know what your fluid is. What is the makeup of that brine? Does your brine contain any old residual oil? Even if it is an injection area for saltwater disposal, does it have any oil in it? If it does, you've got to know how it's going to react with the CO2, because you will get some swelling generally with your oils in there, and that can change how the fluid is going to flow through the rock. So you have to have a sample of the actual fluid in there, and you also need to know what's the chemistry of the CO2 stream. It's not always 100% CO2. Sometimes you get a few little minor things in there that can react with the various components in the rock. So once you have this information, we start to get our lab data, which is right here. And all of this, our seismic, our lab data, the pristine rock and fluids data, the CO2 sensitivity on how they react together with the CO2, the rock, and then the brine itself, and then the seal assessment, all of that goes into models. And what I have emphasized over here is a structural model, a geomechanical model, And that is what are the primary stresses on the rock. When you put CO2 into the subsurface, what are the stresses that are going to dictate where it's going to flow? It's going to go to the less stress regime. That might be up, that might be lateral, that might be slightly at an incline. It's always going to go in the up direction. It's going to try to follow that. So you have to know where those stresses are, which way is it going to go, and then try to predict that. So all of that goes into these geomechanical models. Then you do sensitivity assessments. If we tweaked one thing, how is it going to change the outcome? So those are your sensitivity models. You end up with a high resolution model. Then you start looking at, well, what are the pathways to get this out of it or to allow it to leak? Orphan wells are one of the things you have to look at. What are other pathways? Are there minor faults? Jim pointed out some stuff that might have a fault on a log. Maybe it's not large enough to show up in the actual seismic. So these are, all of this has to come together, and then you do your injection scenarios. So just very briefly, we condense it down to three things: the storage characterization, how many megatons of CO2 will the reservoir hold? What do we think it will hold? How easily will the CO2 be transmitted into and through the reservoir? That's the first part of it. Cap rock integrity. You've got to know whether or not the rock above it is going to hold the CO2 in place. So what's the maximum pressure before the cap rock is breached? Because you have to stay below that in 70 to 80% depending on which guideline you're using. What is the maximum pressure before damage occurs in the reservoir? This happens in the Miocene sands, these unconsolidated sands. You put too much pressure in there, they're going to sand out. They're just going to blow out sand. So you have to know where you're going to damage your reservoir if you put too much CO2 pressure into it. And then what's the containment and the conformance of it? Are there pathways for the CO2 transmission to the surface or into the drinking water? And you know, you look at CO2 and go, yeah, but you know, that's Perrier if it goes into the drinking water, right? Perrier. Great, except that with the CO2 going through those mudstones and the limestones and everything, they pick up trace metals, zinc around here. You don't want that in your drinking water. You don't want arsenic in other areas. You don't want that. Even in trace amounts, you don't want it. So it sounds great. Hey, it's just natural bubbling. We can sell it. Yeah, no, you can't. So you don't want that in there. And you know, I make it sound like this is a real problem. It's not generally. There's not a lot of leaks out there. It's usually pretty safe before it ever gets to that point. How sound are the models with time? We're looking 100 years down the road. We have no idea what's going to happen in 100 years. So we have to rely on the models, and the models have to be based on sound data. You can't just say, oh, we think. We have to know. And is the CO2 going where it's predicted to go? There are a lot of people out there that tried to do water floods and it's not working because it didn't do what they thought. So same thing is going to happen with CO2. So the models are only as good as the data you put into it. So the better lab data you can do, the better it's going to be. And what we're trying to do here is we're trying to decrease the risks and the uncertainties. And the common denominator for these risks and uncertainties and to decrease those are the laboratory measurements. And those measurements are looking at the pristine rock and fluids, looking at the interaction between the CO2, the fluids, and the rock, and then also making sure we have enough physical and digital twins so we can replicate it or we can do it in timing. Some of these we will soak a rock or we'll treat a rock with CO2 for 1 week and test it. Once we treated it and test it to see how it'll fail, you can't go back and reuse that. So you've got to have twins or triplets or quadruplets very similar to almost identical rock types that where you will age one for a week, you age another for 2 weeks, another one for 3 weeks, another for 4 weeks, and we'll go as long as the company wants to pay us to do it because we get money for that. But it's necessary to see where the critical failure might be. Is it 1 week? Is it 2 weeks? Is it 4 weeks? Is it 3 years from now? Nobody's going to pay us to keep something a year. We've tied up our equipment for our pay us for 3 years. We've tied it up for a year before, but never for longer than that. We make a lot of money when we tie our equipment up for a year. Okay, so that is the laboratory measurements. All of this is in place basically to make sure that we are safeguarding the drinking water aquifers and the public above that. We haven't had any deaths from these leaks. There have been people going to the hospital from a CO2 leak out of a pipeline, the Denbury one in Mississippi. That's the anomaly. That is not the norm. But it does happen. It did happen, I should say. Not does, but it did happen. So those are things that we're trying to protect the public and trying to protect the drinking water aquifers. And to do that, the US EPA has a list of guidelines. They have a document about this thick, and I've actually gone through that document. When we first started looking at this with SLV, I was called by our group, our headquarters group, that said, hey, can you look at this for us? Or I volunteered, I don't know, probably stupid enough to volunteer. But I went through the document page by page and identified everything that I could see that I thought pertained to lab analysis. And it is quite extensive, and I did put the document number up here. And by the way, if you guys want a paper copy of this or you want a PDF, send me an email and let me know. I'll send you that PDF of it. And I left off one of the guidelines. There's another guideline up here that's related to logging that is also on here. So what we're really looking at is what objectives are they trying to do, and there's a long list of those objectives. How those objectives are important, whether it addresses the storage, the integrity of the seal, the injectivity of it, or even the monitoring of it, and then whether it's injection zones or confining zones, and then whether these tests are from our determination, whether it can be done from cuttings, from sidewall core or whole core, or do we need fluids, and then what regulation applies. So with all of that, we have worked out a workflow. It's very common across the industry, across the various labs. It's not that unique to us. It is a little bit, but not that unique. Other labs also do this, but for SLB, the coring is very important. You have to have core or cuttings. There is no substitute for whole core. It might be a whole lot cheaper to take sidewall cores and a lot cheaper to get cuttings, but there is no substitute for whole core. You get so much more real estate. Huh? Amen, yeah. Preaching to the choir there, Jim, right? There is no substitute. You learn so much more from whole core that is very important. And you get the real estate to make sure you have enough material to do these physical twins that you need to do it right. So we also have to have fluid sampling. That has not been talked about a lot. You've got to have those fluid samples. The monophasic fluid, which is what's in your brines. If you have any residual hydrocarbons, you need to know that because you can have that swelling with the CO2 depending on your hydrocarbon. And then you also need to know the CO2 stream, what the chemistry of that is, and that's usually provided to us. And then we go into geochemical models and replicate that as far as what's going to happen with the sensitivity. Then you put all of this into the workflow, and I know that I'm not addressing a lot of scientists here, so I'm not going to bore you with that. There is a workflow. It is addressed in detail. And so how all this fits together is basically that table I just had and the workflow I just had fits together right here. So it all goes together to address that. And the first thing I want to talk about is cuttings. The things that are usually ignored. Those little bitty bits and pieces of the rock, the debris as you drill through the rock, the mudloggers who don't get enough praise for what they do. They work amazing hours and look at this under a microscope with blurry eyes sometimes just to see what it looks like. And we can actually tell a lot from cuttings, and it doesn't matter the age of the cuttings. You can have stuff from 1904 or 1906, whenever the field started here, and it's still valid. Those cuttings are still valid because we're looking at the fluid inclusions in them, and we're looking to see if there is a good seal. And the cuttings can tell us whether or not, well, it actually tells if there is not a seal, and that's what's important. If it's not a seal, don't waste a lot of money on it going forward, because you've already proven something that it's not going to get, it's going to be harder to get a permit if you can show at some time in the geologic past that there was a breach of that seal, and you can do that with cuttings. So that's just something that's pretty easy, it's pretty fast to do. Also, we look at the heterogeneity of the rock, and this is the pristine rock. Heterogeneity just means how uniform is it. Are those little layers of shell, sandstone and shell that Jim was talking about, or is it more of a very thick sandstone with maybe a few little baffles of shell in it, or any of that in it? So we do this with continuous measurements. We also look at lab analysis, fracture analysis, and then geomechanics, and then we tie all of that back into the logging program. Something that is also very important is looking at the CO2 brine rock interaction. how do the rocks and the fluids react to one another? What's the sensitivity to there? And one of the things you have to understand is what's the solubility of carbon dioxide in the native brine, or whatever's in the rock at the time, or what's the solubility of the brine in the CO2. Both of those can be affected by several things like temperature, pressure, and salinity. So you have to know what those are in order to understand what the actual solubility is. Also, mineralization and precipitation. Both of those are very important, and I'll just go through this very quickly. We look at the pristine rock, we look to see how those changes will take place, and what we do is we look at the rock first before we've ever treated it. We look at it under a scanning electron microscope. This is the top left image is 4,000 magnification, so 4,000x magnification. It has some false colors. Both of these on the left are 4,000x. It's the same color, the same image, but this one has had a false color attached to it to show the various chemistry in the rock. These are milled using an argon ion mill that actually planes it, makes it very flat so we can see the surface of it quite well. Then we look at it under an energy dispersive X-ray system to actually figure out what the chemistry of it is. And then from that, we would take the rock, actually take a little wafer of it, we treat that wafer under CO2 conditions, and at this point it was only at 300 psi and 115 degrees, so it's not super critical, but it is under some conditions. This happened to be from the Bakken. This was the seal, one of the seals in the Bakken, 20,000 ppm. And I forgot what his time, this is Jimin Liu, he's a colleague of mine, Dr. Liu. He did postdoc in University of Texas, the Bureau of Economic Geology, and this is one of his research. This rock, or this mineral right here, which I believe was a feldspar, I can't remember now what it was, feldspar right here, it dissolved. You can see that it simply dissolved with the CO2. And this right here is a calcite, so it's a calcium carbonate, which makes up limestone. It had precipitation. So you've got dissolution, 10 microns away, you had precipitation. This happens. It happens very quickly and in very short distance, aerial distance. But just to show why this is important, you need to know what's going on. And this, I also can send you that reference if you want it. So the next one is advanced geomechanics, looking at the geomechanics. And geomechanics is breaking the rocks. You put them in a big, it's called a load frame, you push down on it, you allow a lot of pressure, the instrument allows a lot of pressure on it, and that will break the rock until it actually fractures. We want to know at what point is it going to fracture, so that we're not exceeding that when we start to put pressures into it. And what happens is in a pristine rock, the pressure will build up and it will break catastrophically. It breaks, boom, it's a brittle breaking, it's done. We've all seen that when we've bent a stick and it snaps. But if you want to make that stick bend, if you want to build a basket, you put those reeds and everything into water and you soak them. And they soften up and now you're able to use them to bend. You're bending them without breaking them. The same thing happens in the brittle rock when in a lot of these. When you subject it to CO2, and this is after aging, and I forgot again how many days this one aged, but after aging, it becomes more plastic before it fails, and it's a drawn-out failure on it. So it's important to understand all of these parameters. So now, I want to switch over to digital analysis. And I'm almost done. I've got a few more slides, and then we can have lunch. Oh, still ahead of schedule. Great. When I was timing this, I was like way behind. So anyway, the use of digital analysis in all of this. As I said earlier, when we are talking about the laboratory, sometimes this analysis can take, well, it's not sometimes, if we're looking at measurement of CO2 into a rock by flooding the rock with the CO2 under the right conditions and pressure, we may have to do that for a period of a month or 2 months or 3 months to see the result. Most companies are not willing to pay for that. Aramco, yeah. Qatar, yeah. They have a lot of money. Most of the companies in the US are much, much, much smaller. They don't have as much money and they don't have the time. And so they don't want to pay us to tie up our equipment. So what we do is we get the basic data, the actual physical data, then we take the rock and we put it through CT imaging. Well, that's the first thing we do. CT imaging is a computerized tomography, the same thing you do if you want to look at your brain. The same thing in the industry, the medical industry with CTs. We have 2 medicinal grade CT imagers in our lab. We start out with that, and then we look to see, well, where can we go and look at it in a smaller scale? Because the resolution on that is great for your brain if you want to go to a very high level on it. But we're not paying for one of those instruments. We don't need to go that high. And so we actually will then, if we need to go into that nanoscale, that very small scale that Jim was talking about earlier, with these smaller pores, these micropores, we go into micro CT. And from there we have a rock that may only be this big instead of a big core or even bigger rock. We'll do micro CT. So now we're looking at the micro scale for those actual pores where the fluid, the CO2 and the water will be. Or we'll go even smaller into the nanoscale with our scanning electron microscope. So we have all of those scales. Now most labs have all of those scales available. So we look at this. Once we have the physical data, we then take the physical data, put that into our modeling, our simulation model, pair that with the actual micro CT data that we have. And the micro CT data, because it takes a slice of an instrument or it goes all the way through, a slice of a rock or it goes all the way through it, whether you're using scanning electron microscope or using micro CT, you build a 3-dimensional rock model. And that 3-dimensional rock model, we then feed into it the actual geochemical and other data. But if we look at this, this is a 3-dimensional rock model. This is on a nanoscale, but it can be upscaled if it's done properly, and we have proof that it works. The white right here is, it's a little backwards in the way you image this. The white is the rock. So that's the solid rock. The red and the blue are the pore spaces, and you can see how connected in the nanoscale these pore spaces are. So some of these are clays, some of these are larger pores, but the red, everywhere else, red is always gas. In this world, red is oil, and I keep trying to get our modeler to change that. He's from Russia originally, and when they designed this, they used red. And I'm like, in the US, we don't use red for oil. We use red for gas. And it's like, no, I'm not changing it. He's a wonderful modeler. He's very stubborn. And we have so many publications now in these colors. That's the way it just has to be. So this came out originally from our Moscow research lab. They do absolutely excellent, excellent research in that. And this took years to develop. It is the state of art. It truly is different from what you see in some of our competitors because it goes down into the atomic, almost the atomic scale with looking at the chemistry. I've seen the modeling in this use 39 different components in methane alone and be able to use that to model and how is that going to affect the actual, when you're putting methane into a rock. This happened to be the eagle that we're putting it into to see what was happening with EOR. And it is very, very effective when you actually go all the way down into that scale. So it's a very high resolution simulation that we use, and I want to show what it actually looks like. This happened to be one where we put CO2 into an oil and water core flooding. It was a water flood, I'm sorry, it was a CO2 type of environment where we actually can simulate how the red, which is the oil, is being pushed away from the pores and being replaced by the CO2, and then how the blue, which is the water, is also being pushed away and replaced by the CO2. This happened to be an EOR application, but it is the same application that would be used to simulate what would go on in this underground storage. And also, you can take this and move it forward, not necessarily by time. We can't say what's going to happen in 25 years. But we can try to determine what the chemistry changes will be in 25 years, what the porosity changes will be in 25 years, and then model it using that. So by simulating what we think this is going to be, we can figure out what's going to happen in 25 years or 100 years or even 1,000 years if you want. Again, it's a model. Models are based on whatever you put into them. But this is pretty slick, actually. I love looking at this, and I've seen so many times when it really has worked well. All right, so the reason it works well is the degree in which we actually go to make sure we have a representative sample. And it's just going from one image resolution to another, a lot of back and forth where I talk to the person who does the modeling. As I'm a petrologist, trained as a petrologist, a geologist, and we go back and forth and say, no, that element or that mineral cannot be in this rock. And so you then tweak the model to make sure that you have the right chemistry in there. If he's telling me it's got olivine, it's a sedimentary rock, it's not gonna happen. You know, it's like, no, that magnesium or that iron's going somewhere else. It's not going into olivine. All right, so now the last one here is lithium. This is my teaser. I do not know if you have lithium in anything you have here, but I've been involved in quite a few lithium projects now in looking at them from the lab side and from the geological side. Lithium is a critical mineral, and if you look at the global end use for lithium, in 2013, batteries made up 22% of the end use for lithium. Ceramics and glass, which is one of the biggest uses in just 10 years ago for lithium. Fast forward that to 2023, batteries are 80%, and the ceramics and glass is only 7%. It doesn't mean we're producing less ceramics and glass with lithium in it, and it imparts a certain strength to the glass, and it imparts a certain temperature ability of the glass, and also for your UV type of applications. It doesn't mean we're producing any less than that. It means that we're producing a whole lot more of the other, and so it is taking up a very large percentage of it. And I will also say with some of the lithium areas, the one out in Clayton Valley in Nevada, this is something that they're just now proving up. And GM, General Motors, has bought all of the rights to the lithium from that lithium project by Lithium Americas. They bought all the rights. Everything that they produce over the next however many years is going to go to GM for the the EVs that we have. And that is because our industry is moving towards the EV cars. I certainly hope, I was praying that when I rented my car at the Tulsa airport, they didn't give me an EV car because I have no idea how to recharge it. I really don't. And I'm like, oh, I'm supposed to do what? I know you plug it in, but you gotta have the right plugs. And nowadays, most of them are by the apps on my phone, and I'm hard pressed just to get my company apps working on my phone. So yeah, I can do it, but I don't really want to be bothered when I'm renting a car. So give me an internal combustion engine any day. But I am the dinosaur. I hate to admit that, but I am the dinosaur, you know. I will eventually probably, if I live long enough, have an EV. They're great for gas mileage. Well, because they don't have any gas mileage, you know. They're great for, I guess, with the charge. But anyway, so that's enough of that. Supply and demand. EVs are creating our demand. And it has put that into overdrive, I guess a pun intended there. But if you look, this right here is electrical vehicle demand between now, or actually between 2019 and 2030 for lithium. This is what the demand for electrical vehicles, this is everything else. It is rising rather rapidly. And the problem is the demand is far exceeding the supply. And so the supply that we know about is this bottom blue. The orange is possible tons. We think we know, you look at your reserves, you think you know, you have it there, you got similar ones. So that's your orange. Your brown is like, well, we really hope we can find more. So that's your probable additional tons. We're hoping to find more. But this is the demand. And there's a big gap here. And that gap is our shortfall. And that shortfall is only a few years away. It's our lifetime, easily. It's our children's lifetime, easily. It's only a few years away. So in order to meet that, we have to come up with more lithium. And in order to do that, you have to understand where it's found. It's found in lithium-bearing minerals, usually in pegmatites. You don't have any of those around here. Sorry. Maine has some fantastic spodumene crystals that are about 9-10 feet long. Nevada had some that are about 15-20 feet long. Those are great sources, but they're not very common. Lithium-bearing minerals in the sedimentary rocks, those are also great sources. Takes a lot to get it out, but it's a huge source for it. You don't have those here either that I can know of, that I've seen. They have lithium in brines, and the salars are those big, vast salt lakes that you see in Chile and Argentina, even the Salt Lake and the Gray Salt Lake and the playas that you have over in the Basin and Range province. Sorry, but you don't have any of those here either. But you do have oil-filled brines. And that's what I wanted to talk about. And that generally involves something like a direct lithium extraction. And that is what's happening right now in the Smackover in Arkansas and Louisiana. Exxon and a few other companies are involved in that. And that's with usually the direct lithium extraction. Smackover, you don't have the Smackover here, but what you have is you have some shale reservoirs. And if you look in 2022, a professor at University of Houston, this paper or this little article from 2022 said shale reservoirs could be a substantial source of lithium. And just, I think it was last week, one of the Oklahoma City news channels, News Channel 9, I think it was Oklahoma City, company planning to build lithium refinery in Oklahoma. So there is oil-filled brines here in the state of Oklahoma that are being looked at and targeted for lithium. And is that applicable to the Osage Nation? And I say possibly, and I'm saying that with a huge amount of caveats because I have no idea. I could find nothing that gave me any kind of geochemistry in the fluids, in these brines, in this area. So it's something that is an area to look at. And what you do have here is you have the Mississippi lime and you have the Woodford. A little bit of the Woodford, but you have it, and you have the Miss lime. And elsewhere in the state, they are known to have lithium in them. So those are two elsewhere in the state and elsewhere as well. It's known to have that. And this, by the way, is from the American Chemical Society, one of their papers that showed that. So it's something to look at. It's a teaser. I have no idea if it'll play out or not, but you got to start with an idea. And this is where it might be. So with that, I'm going to stop and say thank you. And I think we still have time for questions and lunch. Yes.
So that plant that they're gonna build is supposedly in North Tulsa?
I have no idea, I'm sorry.
That's what they announced, I think, last week.
Okay, I know, it was very recent, I was just looking at this just the last couple of days, I was like, oh, cool, I found something.
They haven't announced, I don't think, exactly where it is, but they were, it was, I can't remember what I saw it in, but they were talking about it. So, I mean, we have lots of salt water, which we do, but it has to come out of the Mississippi line.
No, it doesn't mean it has to come from that, but it has to be something that has a source that has the lithium in it. And that source is generally some kind of salt zone, like the Smackover, the source is the Luan salt, which is what you have in the Gulf Coast. In the Marcellus, which also has a lot of lithium in that is probably the Salina salt, because there's big salt deposits under there. You don't necessarily have those salt deposits here, but you do have material that is being shed into these formations that have lithium in them. The clays sometimes will have lithium in them, and it's a trace element. We don't know enough about where it's really found because nobody's bothered looking at it because it's a very light element. It's very hard to detect lithium. You can't do it through X-ray diffraction or X-ray fluorescence. You can do it with minerals that contain it with X-ray diffraction, but not through X-ray fluorescence. You have to have, you either have to look for a proxy or you have to have a laser-induced breakdown spectroscopy going on it. And the laser-induced breakdown spectroscopy is also called LIBS. They're expensive instruments. Some are very good, some are not, but this is some of the things they've used that was helped to develop or was being developed also through NASA. I know that there are companies that are doing really well at it, and they're trying to develop their own, but in trying to get one of those good lids and get the company, I've been working very hard. It hasn't happened yet. We are looking at buying a lids, a little handheld, but they're about, up to 60 to 80,000 for just this little instrument, and you have to have a reason for it. Or, it's just a toy, it's an expensive toy, and companies frown on expensive toys. So not all brines will have that, but if you don't send it out and get it analyzed, you will never know.
Has anybody tried that building in me,
No, the only thing I've seen is somebody trying to find gold. They will serve right.
They try to do that in the ocean also. So yeah, they can do it. There's trace amounts in the ocean if you have a big enough filter. Yes?
So thank you for your presentation. I learned a lot from it.
Oh, good.
I like it. So one of the things you make me think, I don't know the church said it, is this carbon capture and sequestration
Yes.
in the United States, and how long have they been here on land as far as being just a place that CO2 doesn't die?
Minn Kota has been, Minn Kota, it's up in Illinois, I think it's Illinois. That has been used now for about 20 years. They quit producing, they quit injecting into it, and they're just watching. That's also a research site to watch what happens. So that's definitely on land. That is the major place where they're doing it. They have others in other areas that are still being used, they're still being analyzed. They do have one, it's offshore, but it's in Norway, it's Sleipner, and that one was, they started injecting into that offshore, and that was not into a sandstone, the loose sands like we have here. It was into, I forgot what it was into, Sleipner. Was it carbonates for Sleipner? Does anybody know what Norway Sleipner was? And that one, they are reproducing some of the CO2 from it, but that one also showed that it holds for 20, 30 years without any problem. So they do have some that is done, but the one in Minn Kota, M-I-N-N-O-K-A, I think is what it is. You can look up that one. That's a Department of Energy site. It's a research site also. And that one you can look up. All the data is available online. Sure.
So you, through your presentation, as the person that is involved in the industry, like maybe realized, and I think I knew already how technical the storage and all the research that needs to be done before you inject the design for this. How's your confidence level with our federal government analyzing the applications? And maybe that's not a fair question to ask.
You know, this is my own personal opinion. And I have been involved in the environmental industry before I went to work with SLB, where we had to get application permits approved through both the Bureau of Land Management and through local Department of Health for, not for CO2, but just for doing what we were doing. Plus I also worked in the uranium industry where we had to get applications approved. And what I found is it varies by the person. It's like having a tax accountant. Some are very good and some are not, and it varies by the person. And some have, I don't know, some kind of personal thing they want to go after, and that's what they honed in on, and others don't. So it varies, but what I have seen is that for the most part, the competency of a lot of these federal governments, they are truly competent. Sometimes they're a little short-staffed, a lot short-staffed, and therefore they're doing a whole lot. And that can also be a problem.
You know, as the landowner, as the owner of, and just outside our bedroom window, we've dealt with, as a tribe, we've dealt with federal government a very long time. So we see the incompetency there, and this is a new thing, and it's like trust us. So, and then trust the government again. So,
But
there's issues with us.
if you've done your homework and you have done the proper analysis and you've seen what that can do and you truly believe, you have to rely on your experts.
Absolutely.
And if you believe your expert has expertise in it, then you can move forward. And if there is an issue, then you can say, hey, this is what we truly believe, and here's why. And you can make a case for it. But, do I believe? I mean, I have my own personal opinions on that, but I have not had too much of an issue with competency levels there. It's always been a single individual here or there that would give a problem. Yes, sir.
Dr. Hill, as far as high rate injection CO2 storage, say 40, 50 plus million a day, has Schlumberger's model been able to replicate that with what's going to happen now,
I don't get involved in that end of the models, but from what I have seen, they are able to simulate what will happen in these zones, yes. And what actually is happening is you have a lot of dehydration going on because of this temperature change, and it's actually pulling the water out, it's sucking the water into the CO2, and then you're left with salt behind, and so you start getting this salt precipitation. And then as you move forward, and this has also been shown elsewhere, you get that dual flow where the water goes into the CO2 and the CO2 goes into the water. And so you start to see those changes. They have been able to simulate that and replicate that. But as far as the actual injection rate, I can't say what it is because I haven't been involved in that.
Okay, yeah, I was looking more at the nodal phase.
Yeah, there are people, if you send me an email, I'm more than happy to connect you with the people that are doing those.
Thank you very much.
Yeah. And my email address is right here.
Thank you.
Yeah, thank you. Yes, sir.
So close to me.
Thank you.
So firstly, thank you very much for a very comprehensive
I can walk.
CCS process.